Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to do a topic in mathematics that is under indices and logarithms, and specifically we are going to look at indices. This topic, of course, of indices and logarithms is very important because it's applicable both in physics, especially on the topic of radioactivity. And even in biology, we are going to learn about maybe bacterial decay or maybe exponential growth. So for that case, it's going to be very important because as we come across to such a kind of concepts, we are going to apply this concept of indices and logarithms to try to find some solutions to such a kind of a problem. So for that case, thank you and welcome. So as I've said, today we are going to learn about indices. I mentioned that of course, not sometimes, basically this topic is indices and logarithms. This is usually combined because one is an inverse of the other, as we're going to see. But because today we are going to limit ourselves to the discussion about indices, we'll just leave it at that. So for that case, we start by definition of what an index is. And or in simple terms, an index refers to an expression. This is an expression or a mathematical expression that can be expressed in the form of, so we take an arbitrary number, maybe a, and then there is an exponential there of n. So in this case, the n can imply n number, maybe positive or negative. Of course, plus or minus 1, plus or minus 2, etc. So in that case, the number n replies to a power. Power means that that number a has been raised to a particular, of course, power in that case. And it can as well be referred to as an index or an exponent of a. So when an expression is written as such, then we can say that is a raised to power n, or as the variable a is raised to a power of the number n. Now, using these ones in the mathematical expressions, of course, using numbers, or we can get different expressions from the simple definition of index that we have given. For instance, if we have n, the value of n, of course, as 1, maybe n is equals 1, then we find that the exponent of a to n will give us a value of 1. If it's a raised to 2, this is just a. A raised to 1 is a, and then a raised to 2 implies that we have a times a raised to 3. So as the value of the exponent increases, then you'll find that that particular number is multiplied by the same value. So we find that this value of n can be increased to a very maybe large number, and then that expression will be given as a raised to n. So it is just starts from the initial a times a times a n times. So in that case, other expressions that are expressed in this form that we have said, general expression for an index or an index which is given as a raised to n, can be given in this form, of course. Now there are specific rules which are given, which need to be satisfied in order to express these indices that we are talking about. And of course, these laws, as we are going to see further, they are going also to be applied in that topic that I had mentioned about logarithms, because there's a close relationship between logarithms and indices. So as I have said that if the expression is given as a raised to n, and that one implies that it is a that is in raised n times. So that is rule number one. If it is given in this form, then it is a raised to n times, whereby n is a number. And in any case, of course, I had given a general formula that if n, implying that n is 0, or a positive minus 1, positive minus 2, then we have some cases whereby we can have a raised to negative n. We refer that one to as a negative power. Negative power. So conversely, this one will be referred to as a positive power that does not contain a negative sign. Now there's a special way in which we can represent this, of course. Whenever a number is a negative power, then it can be written in the form of a fraction as 1 over a raised to power n, and the negative sign disappears. So in that case, this a raised to negative n is similar to 1 raised to 1 over a raised to n. Now suppose we had a number for n, and say that is a raised to negative 3, and this one can be represented as 1 over a raised to power 3. Suppose a is equals 2, then we can say it is 2 raised to negative 3, which is equivalent to 1 over 2 raised to power 3, which is 1 over 8. So that is the expression, the general expression that we're going to use. So this is rule number 1, this is rule number 2. So for a negative power or a negative exponent, this is the general rule that we're going to use. Or in any case we find one, then we're going to just convert it using that format. Then when I was giving this n can be 0 plus minus 1 plus minus 2 etc. Suppose the exponent of a is equals to 0. A 0. Then what would be the value for that? So in that case, a number that is raised to a 0 power, we just give it 1. So if a maybe is 5, then 5 raised to power 0 is equals 1. So a number, even if it is b raised to power 0 is equals 1. So that's another rule, that when a number is raised to the power of 0, then the answer to that one is 1. Suppose this exponent is a fraction, then how are we going to represent it? So let's look at that example. So that is another rule which we are going to state, rule number 4. Suppose a has been raised to a fraction, so a 1 over n. And how do we represent that one? So that one implies the root of n. So that one, when it has been raised to a fraction, suppose it is maybe 100 raised to power 2, 1 over 2, and this one will mean that it is the root of that one, 100, which is actually the square root of that, which will give us, of course, we can give an absolute value, but we said it can be either positive or negative, then depending on what kind of data we are dealing with. If it's a whole number, maybe something like a population, then we'll have to have a positive value. So in that case, this is the rule as well that is going to apply for fractional powers, in that when you raise a number to a fraction, it is the root of that number. So in all mathematical applications, these rules apply, and we're going to see that from the rule number 1 that we had mentioned Suppose we have a mathematical equation of this form: a raised to power m, the product of a raised to power n. So here I'm trying to multiply two exponential expressions, that is m raised to power n and a raised to power n. Now to find the product, this is a rule that is product of powers, that is a product of powers, and generally we are going to give this one as a m plus n to the exponent of m plus n. So as you can note, there's a characteristic in the solution in a sense that we have added m plus n. So whenever we have a product of two exponential expressions, then we are going to get the answer as that particular number and the sum of the exponents. So that is for multiplication, or the power of a product. So suppose I give a figure, you can see this is 2, so 2 raised to power 2, and then multiplied by 2 raised to power 3. So the product will be 2 raised to power 5. So if we do just a simple multiplication, this is 4 multiplied by 2, this is 8, and we're going to get this one as 32. So 2 to 5, it is 2 times 2 times 2 times 2 times 2. So this is 4 times 4, 16 times 2, 32. So the product is the same. So for that case, whenever we have two indices or these expressions, exponential expressions that have been given, which are the same, of course, we shall have to add the powers. Suppose this was not a multiplication but a division operation, a raised to m over a raised to n, and this one will be equivalent to a raised to m minus n. So whenever we divide these exponential expressions by the same kind of an expression but a different power, then we do a difference of those powers. Of course, that is the quotient of powers, and then we will find the answer. So suppose we had an example like 2 raised to power 5, where maybe m is 5 and n is 3. So 2 raised to power 5 divided by 2 raised to power 3, then we will have the answer as 2 raised to power 5 minus 3, which is 2 raised to power 2, which will give us 4. So in that case, that will be the answer, and this is the order of the operation that we are going to do. So in this case, we are going to be very careful in that it may be, as I said, that the powers or the numbers representing n can either be positive or negative. Suppose we had a negative number at this point. Suppose n was negative, then we will have to indicate here that it is m minus, because it's a division, and then negative n. So this one will give us the answer of a, of course, m plus n. A negative sign times a negative sign is equal to a plus, so it's going to give us that kind of an expression. So in that case, because this is a positive minus, so suppose it was a minus for m, we have minus m and then n. So this one, as we have said, this one will obey the rule that we said, that is a fraction. So it will be 1 over, because of this negative sign, an plus am. So that one will be the, no, because the numbers which have been raised to an exponent is the same, of course, we said. So that one will be am plus n. This one is already a positive, So we shall have to change this one to a positive because we have changed it into a fraction. So it will be 1 over a m plus n. So suppose it's an exponent or an expression, an index which has been raised to another power. So suppose we had a raised to m, and then this one raised to n. Then that one we're going to find the product of the exponents, which is going to give us a raised to power m times n. So suppose we have a power that, an exponent that has been raised to a particular power, then we are going to have that one. And we're going to look at the distributive rule. Suppose we have different numbers in between here, but for now, that is how we apply that kind of a rule. That is power over power. So for example, we have 2 raised to power 3, and then it's a square of that. So we have to write this 2 raised to power 3 times 2. So it's 2 raised to 6. So that one will be the implication of that. And then suppose we have a same power but different of course numbers, the way I see it. Let's look at this. Suppose we have the number a raised to power n and b raised to power n. How are we going to represent that one? So the power of products, these are 2 products that are having the same power, then we'll have to write it as ab raised to n. So we're going to talk about the distributive rule, and in this case this is the power of the product, and we have the same exponent which is nn, so we just write ab raised to power n. For example, if a was 2 raised to power 2 and then b was 3 raised to power 2, and then we can write it 2 times 3 raised to power 2. So in that case we will have, let's try to check out, this is 4 times 9, which is 36, and this is of course 6 raised to power 2, which is 36. So we can confirm that answer, that expression is correct. So in that case, that refers to as the power of a product. And likewise, suppose we had a fraction of these 2, which is a raised to n, the same exponent b raised to n, then that one is going to be expressed as a over b raised to n. And for this case, we said that for a fraction of this kind, this is given a condition in a sense that the number b, which is a denominator, is not equivalent to 0, because it will be indeterminate in case if that is the case. So for example, if we have a number like 6 raised to power 2 over 3 raised to power 2, then that will be the same as 6 over 3 squared, which is the same as 2 squared, which is 4. So if we look at this, still we can say that this is 36 all over 9, which is the same as 4. So we can confirm that that expression is correct. So that is how we represent, of course, the expressions which have been given in that form. That is for indices. So in that case, this kind of expressions that we have mentioned, of course, is going to give us a clue on how we are going to deal with this kind of expressions that we may come across in logarithms and indices. And it's again going to give us a basis upon which we are going to learn about the logarithmic and exponential functions. So as I said that there's a close relationship between logarithms and indices, we're going to look at some of the basic rules of logarithms and see whether they just apply as we said for the case of indices. And I'm going to give, of course, one of the examples using this. Suppose we are given this kind of relationship of the exponential equations and logarithmic functions. Of course, I've just mentioned that one in order to give the relationship, because if you can see this side of the board, this on our left, I've given a relationship. Of course, that's an equation of x is equals an index that is appearing as a raised to power y. So this one can be given in terms of a logarithmic function, which is y is equals the log to base a of x. So if we try to look at the relationship between the two equations, we can see that, or between this exponential equation and logarithmic function, we can see that for this exponent, this is of y, it appears as a subject of that logarithmic function as such, of course. So in actual sense, when we have been given this number and asked to find the logarithm, it implies that you find the value of y. So that is the relationship that exists between exponential functions and logarithmic function. So in that case, when you convert from an exponential function to a logarithmic function, this particular base, so this is log to base a, so on the logarithmic side it becomes a base, whereas it's just a number that we have said that is raised to power y. So in this case, the x that we are referring to here is a number, and we're going to give some of the expressions to, of course, create an emphasis on that. So in that case, we're going to see that generally there is a way in which we express the log to base of a number, and mostly it is given as log to base of 10. Most expressions contain log to base 10 or log to base e, where e implies, of course, a natural number, which is a constant, or a natural logarithm, which is a constant that we're going to see, of course, which is a Euler's number that we're going to see later. So in that case, we can look at this. Now that we have looked at that relationship between the exponential equation and the logarithmic function, and we have said that one is an inverse of the other, and we can be able to look at this. Suppose we have a number that is log to base 10x, which is given as the value of p. So this one implies that 10 raised to power p is the same as x. So that is the relationship between that exponential equation and the logarithmic function that we have on this other side. So that is how we can be able to convert. And suppose we had another number log to base 10, of course, of y, it's given as q. Then this one implies that 10 raised to power q will be given as y. So from the laws of indices that we had talked about, this is simply like the a that we are giving, which is raised to power n. Then suppose we have x, the product of x and y, which is x times y. That one in terms of the indices will be given as 10 raised to power p for x times 10 raised to power q for y. So this is similar to the expression that we were giving, that it is a raised to power m times a raised to power n. Then whatever we were doing for this kind of an expression was to give the sum of the powers. This is a product rule, so we write it as m plus n, a raised to power m plus n. So in this case, our expression will give us the solution for 10 raised to power p plus q. So if it's a product, then we're going to add. Now suppose it's a number from this expression that we're going to divide, like x divided by y. So if it's a fraction of x over y, then we will have this x over y, and we will have to do a division as we said, so it is 10p minus q. The power of the numerator minus the power of the denominator gives a representation of this particular set of division. So suppose it is x raised to power n. Since we know that x represents 10 raised to power p, then it is 10 raised to power p into n. We talked about the powers of powers, so in that case we're going to multiply the powers and get the solution as 10 raised to power p, the product of pn. So that's how we are going to represent it. That's the relationship between the laws of indices and logarithms. Therefore, given an expression, or given an expression of this kind, let's try to look at this. So given an expression of this kind whereby we have log to base 10 x, y, and we can write this one as a sum of those two products. So log to base 10x plus log to base 10 y. So this one, which is a product of these two numbers, can be expressed to base 10. So long as the base is the same, we're going to have a sum of those two. So similarly for division, which is a log to base 10 x divided by y, or x over y, this is going to be log to base 10x minus log to base 10 y. So and lastly, if we are given a power which is log to base 10, of course, x raised to power n, then we are going to have it simplified to as n log to base 10 x. So which means we have taken the power to be on the other side. So as we have considered log to base of 10, maybe of x, we said it maybe is equals to a particular number like n, and we said that this one can be given as 10 raised to power n is equals x. We can as well look at expressions which have different bases and try to see how they can be expressed. For instance, if we say log to base 3 of 9, which is equals 2. So this one implies that 3 raised to power 2 is equals 9. So for that case, the log to base 3 of 9 is equals 2. And similarly, if we say that we are given an equation which is 8 is equals 2 raised to power 3, then we can rewrite this one in form of logs as log to base 2, 8 is equals 3. So 2 raised to power 3 is equals 8. So that's how we're going to do an interchange, that one from the, of course, the indices to logarithmic functions, from the exponential expressions to logarithmic functions. So in this case, it's a general formula for that, and generally we can say that given a number x is equals a raised to power y, then we can say that log to base a y is equals x. No. So this means let's try to look at this, produce another expression. So for that case, we have given x equals a to the power of 3. As we have said that this particular exponent is the one that gives an answer for a logarithmic expression. So we are going to have it represented as log to the base of a x is equals b. When we are defining a logarithm, we say that it's a power that has been raised, a number that has been raised to a particular power. So it's that power represents a logarithmic answer. So for that case, the log to base a of x is equals b. So we are going to look at other properties of logarithms, of course, which we have made a summary of. And we see that there are 3 basic laws of logarithms which are true when a particular base has been used. So if we are doing for logarithm of a base other than the 10 that we have been using, we'll find, for instance, if we give an example of this, there's a particular procedure that we're going to follow. Let's look at an example for this. Suppose you are asked to find log to base 3 of 7, and then we can calculate this and say that the answer will be x. It's unknown, it's an unknown answer, so let me just try to reduce space. So log to base 3 of 7 is equals x. So in that case, we are going to have 3 raised to power x is equals 7 from that, of course. Then we can as well try to look at this is an expression which is a exponential function or exponential expression. So we are going to also we can find the log of both sides for this, and this is a log to base, of course, log to base 10. We say log to base 10 is a common of 3 raised to x is equals log to base 10 of 7. So this is another way of trying to rewrite an expression that we have been given, which is not log to base 10, of course. And this one, we have written it as log to base 10 of 3x, 3 raised to power x is equals log to base 10, 7. So again, we can try to look at this. I talked about a number that has been raised. When we are trying to find the log of a number that has been raised to a power, and we are given the example and said that this particular power will be taken to the other side. So we shall have log to base 10 3 is equals log to base 10 7. So when we have such a kind of an expression, then we can make x the subject of the formula and write x is equals log to base 10 on the other side. So x is equals log to base 10, this is 7 over log to base 10 3. So if you look at that, that of course is a division. Then this is going to give us an answer by finding the expression for that. So in that case, if we say that log to base 37 gives us x, and we are going to find the value of x from, of course, the evaluation of those 2 logarithms, and we find the answers are equivalent to 1.7 7 maybe to 3 significant figures. So for that case, this is another way of trying to use the log to base 10, trying to find expressions which do not contain log to base. Then of course we can just rewrite it as an exponential equation, or maybe exponential equation, that is in that case, and then use the logarithm to base 10 to try and find that figure. So this is one of the ways in which we can be able to use this kind of concepts that we have learned in order to find a solution for both the logarithmic functions and the exponential expressions that we have written. So as we said, these expressions or the formula that we have discussed can be extended to negative powers, because mainly we have been dealing with positive powers. Now for the sake of for the case of indices, we can just give an example to illustrate what we are talking about, especially when it comes to negative powers. So let's look at this example, or just a general example of a or m which has been raised to power negative p over q. As you can see that, of course, it's a negative power, then we can write this one, all of this power is negative, so we can write this one and say it's 1 over a raised to p over q. So that one, again, we can say when we were talking about a fraction which has been power, of course, fractional powers, we said that as well this one can be written as 1 over the root of q. So this one implies the root of q. So we are going to have the root of q, a raised to the power of p. So if we try to look at that one keenly, and maybe give it just a normal numerical figure, we give these expressions the normal numerical figure and just input numbers for that. We can write, for instance, if it's 4 raised to power negative 3 over 2, and we are requested to solve for that. So this one can be written in this second form that we have talked about, which is 1 over 4, 3 raised to power 2. Since the whole of this exponent or the power function is a negative, then this one is going to be written in this form, and then we say it is 1 over, of course, this is the root, the square root, 4 raised to power 3. So the one inside there will give us, under the root sign, will give us, that's 4 to the power 3 is 64. So it is the root of 64. So the solution for that will give us an 8. And that is the way we can be able to apply this general rule for negative fractional powers in order to solve such a kind of expressions. So that is it for today, guys. I think we have had a meaningful discussion on laws of logarithms and indices. So whenever we come across them, we'll be in a position to try and solve such a kind of problems, or which are related to the concepts that we have discussed. So that one is going to assist us much as we're going to deal with other problems which are related to indices, or powers, and logarithmic functions. So for that case, that is it for today. Thank you very much. Bye. May God bless you.